Dear colleagues, we bring to your attention an article on topic of optimal threshold selection criteria for face anti-spoofing systems. To begin with, biometric identification systems are now really common, providing convenience but also posing new challenges. The rise of automated biometric systems like face recognition has increased the potential for presentation attacks, further PAs. Face anti-spoofing is essential in combating these attacks, ensuring the integrity of biometric security systems. This technology is crucial in various high-security domains where facial recognition is vital for authentication and access control. Security-sensitive areas face greater risks from a range of attacks, including videos, photos from mobile phones, both printed, masks and morphing techniques that blend images to create fake identities, for example using other artificial intelligence tools. These sophisticated attacks demand robust countermeasures for secure and reliable identification processes. In less security-intensive environments like social media and online shopping, the focus of presentation attack detection (PAD) shifts towards balancing security with user experience. The challenge in these less critical areas is to minimize user friction while maintaining effective security until PAD solutions are perfected. Our article is devoted to the problem of error threshold selection. Considering that there is no currently face anti-spoofing system which is completely error-prone, it's really necessary to carefully select those error thresholds. For example, if we set high thresholds, it can cause user frustration and potential abandonment of the biometric authentication process when it's not critical. On the other side, if we set low thresholds, it implies security risks by potentially allowing unauthorized access. To describe how presentation attack detection subsystem works, we could break the whole process into three simplified steps. First one is data handling, where the biometric data from face recognition system is analyzed by the PAD subsystem using a convolution neural network. Then the PAD subsystem outputs a confidence score indicating whether the data is genuine or fraudulent. And lastly, the decisions are based on comparing the confidence score against a classification threshold guided by standards such as ISO or IAC. PAD systems are evaluated by key performance metrics such as APCR, which stands for Attack Presentation Classification Error Rate. It measures the rate at which attack presentations are incorrectly classified as genuine. And BPCR, which stands for Bona Fide Presentation Classification Error Rate. It measures the rate at which genuine presentations are incorrectly classified as spoofed. Here are the formulas to calculate these metrics. It is important to note that APCR metric considers the number of attack presentations for a given presentation attack instrument species. Also, we include here another metric, which is ACER, which is basically the average between APCR and BPCR. As the outcome of the PAD system purpose, attack presentations tend to receive lower scores while bona fide presentations receive higher scores. However, because these scores overlap in most cases, a specific classification threshold should be selected. On this histogram, an average PAD system scores are displayed, and as we can see, there is no way to skip setting a threshold which causes APCR and BPCR to overlap other scores. There are several known ways to set the classification threshold. The most popular and simple one is to set classification threshold by minimizing equal error rate, equalizing APCR and BPCR using training dataset. The downside of this approach is ignoration of the PAD operational environment as well as security requirements. Then what can be done? Experimentally adjust classification threshold based on system requirements. The downside of this approach is the need for manual processing of relevant classification data. And the third approach is to use RIOPAR metric proposed in 2023 revision of the standards which define the metrics for PID systems. It is used to measure how well a biometric system detects attacks without interrupting legitimate users. This metric places user experience and convenience higher in the process of selection optimal threshold, making it barely suitable for security critical areas. Here is the formula to calculate this metric. To mitigate this problem, we could implement an optimal threshold selection formula which could allow us to automate the process. As you can see, we are implementing the environmental adjustment, which is a factor that accounts for variations in environmental conditions that may impact the performance of face anti-spoofing system. It can be expressed as a function of environmental parameters such as general security conditions and requirements, for example, availability of human intervention to the identification process, biometric presentation specific conditions, and other PID product specific criteria. And you can see the formula to describe the environmental adjustment. As you can see, it has the weight assigned to each environmental factor based on its importance and the impact on the system's performance, as well as the value of the environmental factor, which could be positive or negative at the given moment, considering how it is supposed to impact the general threshold. To conclude, our research examines the selection of optimal threshold in face anti-spoofing systems to enhance security and maintain user convenience. We have found that traditional approaches focus on minimizing equal error rates, often overlooking the variability in operational environments and security needs. Most production-ready PID systems adhere to the ISO IEC standards, utilizing metrics such as APCR, BPCR, and ACR to assess performance. But the diversity and the number of spoofing tools make it hard to model all the potential spoofing methods, complicating the fine-tuning of the PID systems. We have analyzed systems like ABC for EU and highlighted the shortcomings of the static threshold settings based on the pre-trained datasets. We have introduced a method for automated threshold selection with an environmental adjustments factor, which consider the deployment context-specific security and user experience needs. This enables us to dynamically adjust thresholds based on environmental parameters, allowing face anti-spoofing systems to operate more effectively and securely in various real-world settings. Thank you for your attention.